So far, when we've been finding derivatives using the difference quotient or using the rules of differentiation, what we found is actually just called the first derivative. And here I've even notated here the different notations we use for first derivative, y prime and f prime from Newton's notation, or dy dx or df dx from Leibniz notation. But there are times in which we want to find the rate of change of a rate of change. If we think motion as an example, velocity is a rate of change, and there are a lot of times we want to talk about, well, what's the rate of change of velocity, or as you're more comfortable with in motion, acceleration. It's not always going to get called acceleration because it depends on the context, but the idea of finding a rate of change of a rate of change is not a rare thing. So if I take the derivative of the first derivative, we call that the second derivative. And its notation, for Newton, we just put another prime. So this would be y double prime, f double prime, and that means the second derivative. For Leibniz notation, we would put a squared after the d on top and a squared with the x on the bottom. And I would read this as d squared y dx squared, or d squared f dx squared. And that would stand for the second derivative, which is the derivative of the first derivative. But then what if I take the derivative of the second derivative? Well, that's called the third derivative. For Newton's notation, I would put another prime in the symbol, so this would be y triple prime or f triple prime. And instead of squareds after the d on top and the x on bottom, I put cubes. This would be d cubed y dx cubed, d cubed f dx cubed for the Leibniz notation. But then if I take the derivative of the third derivative, that would be the fourth derivative. And the derivative of that would be the fifth derivative. And the derivative of that one would be the sixth derivative. I could actually just keep going on and on and on. We don't normally go on and with no end. We will stop at a certain point. Or if we're told to just keep going, we go until we hit 0 for a derivative, or we can see there's a pattern in the derivatives. So an example of this would be if I had the function x cubed minus 5x squared plus 2, and I'm actually asked what's the third derivative of this. So to find the third derivative, I need to know the second derivative. But to find the second derivative, I need the first derivative. So I'm going to start by finding the first derivative, or just as we're used to saying it, the derivative of x cubed minus 5x squared plus 2. Well, the derivative of x cubed is 3x squared. The derivative, then I have my minus sign. Derivative of 5x squared would be 10x to the first. Then I have my plus sign. The derivative of 2 is 0. Now, I will admit I normally wouldn't write the plus 0, but because you're still learning the rules of differentiation, I put the plus 0 so that you understand the 2 didn't just disappear. Its derivative is 0. So now to find the second derivative, I take the derivative of the red. So the derivative of 3x squared would be 6 times x to the first. Then my minus sign. Derivative of 10x is 10. And then the derivative of 0 is still 0. And that's my second derivative. But now for the third derivative, I take the derivative of the blue. So the derivative of 6x is 6. So I have my minus sign. Derivative of 10 is 0. And so my third derivative is just 6.